to lecture number 4 on network analysis, and in our first 3 lectures I introduced to you various kind of sources, means the sources could be ideal or practical, and it could be also either a voltage source or a current source. Only thing you should remember is that ideal voltage source will be represented like this, without any internal impedance in series, okay? And its EMF will be shown in this diagram, and 2 terminals I am just telling A B. So, ideal voltage source should be kept open circuited, okay? And a practical voltage source will be represented like this with its internal resistance, which is supposed to be small A and B. These will be the terminals of the source, and then I told you the current source, okay? And the open circuit EMF is E, and this voltage source should be kept open circuited when not in use. Otherwise, it should be connected to the other network with which you want to energize this voltage source. Similarly, the current source, a practical current source, will have a magnitude of current, specific magnitude of current. This is ideal, this one, without any internal impedance. Internal impedance in case of current source we discussed will be connected in parallel with this, and ideal current source, of course, the internal impedance or resistance is very large. So, it is open circuited, and since the current source will try to drive current in whichever branch you connect in the circuit, irrespective of what impedance you have connected. Therefore, the impedance connected when open circuited is very large, therefore, a large voltage may appear. Therefore, an ideal current source or a practical current source should be kept open circuited like this. Here also it should be open circuited, so that the current will flow like this, and potential difference between these two part will be 0. Mind you, internal resistance is there, but if you keep it in short circuit condition, there will be no power loss here also, because all currents will be flowing like this. So, it should be kept short circuited. Then this current source we have shown is nothing but equivalent to a internal resistance R and an EMF. EMF I am sometimes showing circle plus minus or a battery. Generally, large DC voltage sources are shown with these symbols. Okay. Small battery voltages are shown like that. So, it is like this. Similarly, if such a situation occur, so it can be represented, this I will rather cut it out here. So, any circuit with this thing in a practical voltage source and a load impedance connected R L is equivalent to a current source across A B, whose value will be E by R. These we have discussed, E by R, and in parallel with this resistance R, internal resistance of the battery and then the load resistance. These two circuits are equivalent. We have shown that by parallel conversion of this R and R L, this current, load current here and load current there will be same. Now, only problem is what happens if the So, this way you can go, also you can always transform a circuit having a current source in parallel with a resistance like that, where E by R into R is the, see, these are the terminals. So, if you look from side A B into the circuit through the terminal A B in the circuit, to the user it does not matter whether you are representing the source as a voltage source in series with a resistance or a current source in series with a resistance. External world, that is RL, will never know, can never distinguish between these two. So, anyway, so it is always you can convert it if necessary. My personal suggestion will be, if in a circuit there is current source, live with it. Why unnecessarily you change it to a voltage source? Of course, if you get some very great advantage, you do that, but in general you should not do. Similarly, voltage source, let it be voltage source. But after learning this, then there is the awkward situation will be, you have an ideal voltage source E, no internal resistance, A B. Can I represent it, draw an equivalent current source circuit for this? Because the internal resistance of the battery is 0, and if you want to do that following this rule, this magnitude of the current, internal resistance being 0 here, E by some sort of 0 number, and in parallel we are telling it will be shorted, is not, because parallel this R, if R is 0 here, internal resistance of the battery is 0, then there are awkward situations. It looks like you cannot do it. Similarly, if you have an ideal current source I with terminal A B, and there is no internal resistance of the current source which is in parallel, therefore, it is very difficult to represent it in this fashion, a source and an internal impedance. What is the value of this? This resistance. What is this resistance? This is infinitely large. So, infinitely large resistance here. Therefore, what do I do with this? If you try to convert in this way, you connect anything, this circuit tells me, oh, nothing can be done, because this is an open circuit virtually. Therefore, these are some awkward situations. But I will tell you one thing that you note down very carefully, that okay, if it disturbs me, what I will do in a circuit, if there is a ideal voltage source and current source, first of all, I will never attempt to convert them from voltage to current source or from current source to voltage source, because there are difficulties. Because in case of ideal voltage source, internal resistance is 0. If you want to convert it to a current source, E by that 0 in series with parallel with 0 resistance does not help me to analyze the circuit or the load current which will be connected there. Similarly, vice versa, as I pointed out. But nonetheless, one point I must tell you, that suppose you have an ideal current source I. If that disturbs you, what should I do? If it is an ideal current source, what you can do is this: you can imagine that okay, it is not ideal, I current and in parallel with a resistance. I will just do that, and across AB circuit is connected. AB. Some load resistance is connected. But this one I can convert it, R tending to infinity, this much if you say, then this is the situation. Live with this R value is not known, I mean no finite value. Then what you can do is this, you can convert it to no problem, like write ER here, no, I into R here, in series with R, limit R tends to infinity, like that you write, no problem. There I am feeling comfortable, okay, this is what I can always do. And then your circuit is there, load current you want to find out. Suppose you connect to this circuit a resistance of RL. So, what I am telling, RL you connect, then solve the circuit. What will be the load current? IL. IL will be this EMF, which is I into R divided by R plus RL. This will be the current in this circuit. Is that clear? So, now you say R tends to infinity. R tends to infinity means RL, this R is very large compared to RL. So, this will be equal to IR divided by R, as R tends to infinity, compared to RL it will be large, and this will be I itself. So, what I am telling, if somebody connects a resistance RL, better do not try to convert it. If you wish, you bring this resistance and pretend that it will be infinite, solve the circuit, then at the end say R, capital R tends to infinity. What I am telling, you will get the same result. If you connect RL, what will be the current in RL? Ideal current, so psi over. But this point should be understood. Got the idea? Therefore, if it is disturbing you at all, then pretend that okay, an infinite resistance is connected, then do this and then find out the current, and at the end, so whatever current you find out, it will be a function of this capital R, and capital R tends to infinity. Similarly, a voltage source, ideal voltage source E, these are the terminal E, internal resistance is 0. I want to convert it to a current source, which I cannot if R is strictly speaking 0. What I am suggesting, in that case, you show this resistance like this, E by R, remembering that R tends to 0. This is the correct representation, and then I will say okay, if that be the case, then it should have an ideal current E by R, and in parallel with a resistance R. Now, whatever you connect across A, B, solve this network to get the load current. Suppose RL is connected, solve this network. Then, when you find out this current, it will become a function of small r, IL, whatever IL you will get. For example, this current I want to find out. So, IL will be, in this case it is so simple, this current is E by R, total current. You want to find out current through this branch. So, this into R, other resistance which are in parallel, divided by RL plus R, division of current in parallel resistances. Then you say limit R tends to 0. Try to find out this magnitude. What it will become? It will become R tends to 0. So, this can be straight away written like this, E by R into R by R L, and then limit R tends to 0. What is this value? This will be simply E by R L. E by R L. So, same thing, I mean battery connected across R L, okay. This is the current. And the point I want to make it, in this case I told okay, conversion is not possible. If somebody insists no convert it and try to do it, then okay, imagine there is series resistance R. So, this you can then do E by R parallel R, find out whatever network is connected A B, solve the currents in that network, and then do not forget to take limit that R tends to 0, you will get same result. Anyway, I have made my point, you have understood that. Therefore, this can be solved. Acha. Now, what I am going to do is this, as I pointed out earlier also, that KVL, KCL is the main thing one need to know to solve any given network, to find out currents or voltages across various branches and so on, that is fine. But we will try to use some techniques to simplify our calculations or understanding of the circuit. To begin with, I will discuss these two methods. So, we will be first discussing about two very popular method. One is called mesh analysis, which you know, but let us review those things. Mesh analysis and then node analysis of circuit. And these two I will first do assuming your sources are of constant values, that is DC. If it is voltage source, no time varying thing. Of course, that restriction we will remove after few lectures. So, I will assume some circuits where sources are constant, constant DC values, and only resistances, are present. In networks, I want to find out the currents. To understand this, what I am telling, suppose you have a network like this. Suppose you have a network and there are sources connected. Say this is E1, these voltages may be known and these are resistances R1, say R2 and R3 and suppose there is another resistance here connected. R 4. Okay. And I want to find out currents in the various branches in this network. That is the thing. Now, to solve this network problem, as I told you, I can solve it by assuming this current, that current, applying KCL, KVL in various loops, but let us be methodical how to do it. Now, in this network you find there are several windows like this or several closed paths. For example, this is a closed path, this is a closed path, this whole thing is also a closed path, like that. So, first I distinguish between loop and mesh. So, it is like if you consider this is window, window panes are there. Okay. Now, any closed loop you identify in a network, these are loops. Okay. For example, this whole thing is a loop. Similarly, this is also a loop, this is also a loop, and this is also a loop. But you see, in this outer loop, this bigger loop, there are several sub loops present. In this particular loop, within that there is no other loop present, and when such a thing happens, then we say this is a mesh. For example, this is a closed loop, but it is a mesh. Similarly, this is a mesh within which there is no sub loops. Similarly, this is a mesh. But is the whole thing is a mesh? No. Within that there are several loops present. Therefore, meshes are those closed loop within which there you will not find any other loop to be present. Okay. So, given a network, I can distinguish between mesh and loops. So, this is the thing, mesh. If so, in this network there are 3 meshes. This is 1, this is 2, and this is 3. The mesh analysis tells you that you assume the mesh currents. So, I can say that all meshes are loops, but all loops are not meshes. Obvious. This is a loop, this loop is a nothing but mesh, this is also a loop, nothing but mesh. So, distinction between loop and mesh, I hope you have understood. Now, what you will do is this, these 3 mesh you assign currents, which are called mesh currents. I 1, this current I will say this is I 2, and this mesh currents you say I 3. Okay. These are called mesh currents, which I have assumed. It is preferable because I told you while solving circuit, direction of the currents is your prerogative. You choose any way you like, but since I want to develop a systematic method to solve a network by mesh analysis, I am telling that assume the currents in the clockwise direction like that. Now, what really I have assumed? I have assumed actually this branch currents to be I 3, is not? this current is I 3, has to be, that is what I have assumed. Similarly, this branch current I have assumed I 1, this branch current I have assumed I 2. Got the point? These are the currents I have assumed. Therefore, by applying KCL here, I see that the current from left to right will be I 1 minus I 3, because I 1 is coming, then I 3 is going. So, I 1 minus I 3, or one can say I 3 minus I 1 from right to left, in whichever way you feel you can write it. Similarly, this branch current, this is I got it to be I 1 minus I 3 coming in, and you can apply KCL here. So, this current will be I 1 minus I 2 from top to bottom. This branch current will be I 2 minus I 3 from left to right, and in this branch of course, this is I 3, this is I 2. Also, I will connect at this point, which is not necessary, but let me connect another resistance here R 5 in this network. Okay. So, in mesh analysis, you first identify the meshes and then assign loop currents in a following a particular logic, that is clockwise current I will do. Then what you do? You write down KVL in these 3 meshes. For example, I would like to write down KVL in mesh 1. I will write down mesh 1. Now, while writing KVL, I know this current here in this R 1 branch is, I can say, plus minus, and this drop will be R 1 into I 1 minus I 3, is not? Similarly, this current from top to bottom is I 1 minus I 2, they are opposite, and this drop can be written as R 2 into I 1 minus I 2 with this polarity, mind you, that is very important. If somebody says no, current is I 3 minus I 1 from right to left, if he writes, then he has to write plus here minus here for the voltage drop R 1 into I 3 minus I 1. So, I have done this. Then I start from this point and try to reach this point traversing this mesh. So, from this to this it is E 1, from this to this it is plus to minus. So, minus R 1 into I 1 minus I 3, and from this to this once again minus R 2 into I 1 minus I 2. And you reach here, from here to here nothing. So, I have come back to the same point where from I have started, and KVL says me that this must be 0. So, if you transfer the sides of keep source only on one side, you will find this is nothing but R 1 plus R 2 into I 1, this and this you bring it to that side, minus R 1 into I 3 and minus R 2 into I 2, this must be 0, that is the no 0, this must be equal to E 1. So, this is the KVL equation in mesh 1. Similarly, I can write down the KVL equation in mesh 2, which I will just tell. You see, there is a pattern in this case. What is that? In mesh 1, if you want to write down the KVL equation, there are 3 unknowns I 1, I 2, I 3, because if I somehow can solve I 1, I 2, I 3, I will be in a position to find out the currents in any branch I like, that will come as a difference of these 2 mesh currents, where there is a common element present. In this branch current will be I 1, in this branch current will be I 2, and so on. So, this is the equation 1, but I must form 3 equations. So, this is equation 1. Similarly, in mesh 2, so if you see, there is a emerging pattern. Coefficient of I 1 will be nothing but sum of the resistances present in this mesh, R 1 plus R 2 into I 1. Coefficient of I 2 when you are writing KVL equation in mesh 1 will be, coefficient of I 2 will be the common resistance whatever is present preceded by a negative sign. Coefficient of I 3 is the common resistance whatever is present between loop 3 and mesh 3 and mesh 1, that will be minus R 1. That is the thing, equal to any sources present in this network. Yes, there is a source E 1 and whose positive polarity is such that it helps in E 1 to circulate in the direction I have assumed. Current comes out from this, from the positive end of a battery in general. Therefore, that is why it is plus E 1. Why plus E 1? Because plus of this battery is in the same sense as that of I 1, current sense. So, if that be the case, one can write down once again in the same way KVL equation in mesh 2, where I 2 is present. I will say, look here, the coefficient of I 2 will be sum of all the resistances R 2 plus R 3 plus R 5 into I 2, that is what it will come, R 2 plus R 3 plus R 5. In this mesh, these are the resistances present, that is why I 2. Will there be a coefficient in mesh 2 of I 1? Yes, there is a common resistance, and that will be minus R 2 into I 1 plus this. Then what will be the contribution of I 3? It will appear as a drop in R 3. So, minus common resistance existing, yes, R 3 into I 3, that is all. So, all the drops I have taken, and on the right hand side I will connect, this is plus mind you. On the right hand side I have to check whether there is any source present, in this case voltage source only. And should I write plus E 2 or minus E 2? In this case, see the polarity of E 2, that battery is such that it opposes I 2, therefore, it must be minus I 2. So, this will be equation 2 in mesh 2. Similarly, in the third loop KVL, so this is KVL in this one, and where should I write? KVL mesh 3 will be coefficient of I 3 will be sum of all the resistances, that is, it will be something like R 1 plus R 4 plus R 3, R 1 plus R 4 plus R 3 into I 3, that will be. Then coefficient of I 2, yes, it will be common resistance preceded by minus sign, that will be the coefficient of I 1 in mesh 3. So, R 1 minus R 1 into I 1 plus, will there be a term involving I 2? Yes, there is a common resistance minus R 3. So, minus R 3 into I 2 and this is plus. And the right hand side should be any sources present, those terms will appear, and in this case there is nothing present. So, it will be 0. Therefore, after assigning the mesh currents, you can go as I did for the first equation. You repeat for the second and third loop, showing the polarities, this, that, and then I am telling you the final equation will be like this. This is the thing, original thing, KVL I had applied, noting down plus minus sign, this, that, okay, but finally it will come like that. From where I told that there is an emerging pattern, because coefficient of I 1 will be in mesh 1 you are writing. So, come here, sum of all the resistances will be coefficient of I 1. Coefficient of I 2 will be, is there a common resistance in the common wall between these two meshes? Yes, there is, minus R 2. Coefficient of I 2 should be minus R 2 into I 2. I should have written this term earlier, anyway it does not matter, then minus R 1 into I 3, because there is a common resistance, following the same logic I did. Therefore, you see, writing down of KVL equations, 3 equations you require to solve this, you have been able to write down 3 KVL equation, and for that I should not take practically much time, very quickly I can write if I know this rule, okay, this is what is going to happen. That is the advantage mesh analysis. You generate 3 independent equations, and then of course, these 3 algebraic equations are to be solved. Only one point I will tell, that I can have choose any other loop, for example, the outer loop, KVL will be satisfied. Yes, it will be, it has to, and one can say, okay, I will get another 4th equation, that is not to be. It will also give you another equation, no doubt, but that equation can be, will not be an independent equations. That equation can be generated from these 3 equations only. Therefore, you identify the meshes, write down the KVL equation in each mesh, which following this logic becomes very simple, and you get your solutions. Therefore, how many independent equations will be there? As many meshes are there. So, this is about mesh analysis. We will continue with some example in the next class, what to do when current source is present. Thank you.